Now, in our previous calculations, what we were actually trying to find is we were trying to explore how objects move relative to motion. But we were doing it using graphs and other arithmetic methods. But what I'm about to do now is show you how you can make a shortcut to what we've been doing previously. And that's by using the Suvat equations, or the equations of motion, as you may all know. Now, in general, when the initial velocity is u and final velocity or velocity at t seconds is v, then that means the increase in velocity is v minus u. Now, as we have explored previously, we would know that the constant acceleration is a meters per second squared. We would know that when we are inspecting our graphs, this is what would come up. This would be the change in velocity divided by time, the change in velocity, which means would it be v minus u over t. Now, if we make v the subject of the formula, then our first equation would become v is equal to u plus a t, which would become our first equation. And if you use similar methods to these, for example, we'll use area under a graph. Let's say this is the v versus t graph, and there we go. There's the motion of our object. Now, if we know the area under this line, we could obviously easily use this formula whereby the area is equal to half the base times the height. In other words, the height we know is the acceleration. So our formula would be area is equal to half u plus v times time t. Of course, now we know that the area is in fact the distance as we've done in the previous problems, which is u plus v divided by 2 multiplied by time. This would be our second equation. And by inspection, we can obviously find the other equations, which would also become s is equal to ut plus half a t squared. That would be our third equation. And our final equation would be v squared is equal to u squared plus 2as. And that would be our fourth equation. Now, let us tackle our first example problem.